Okay, so we have a couple more of these to graph. So first thing I want to do is look at my logarithm and see what my domain is. So the value in here has to be greater than 0. So then when I solve this, my domain is x values greater than 1. And that value right there, my boundary, that's going to be my vertical asymptote for my graph right here. Now, I could kind of play around and try to find some values to make this work, but an easy approach is to go ahead and find the inverse function of this and then find a table, swap the values, and plot those points for your logarithm function. So first thing I'm going to do is I'm going to change the function notation to y. So y equals log base 5 of x minus 1 plus 2. Now, in order to transform this into exponent form, I'm going to have to isolate the logarithm. So I'm going to subtract 2 from both sides. And now I'm ready to convert this into exponent form. And so I'm going to have a base 5 raised to a power of y minus 2, which is then equal to x minus 1. Now, this is not my inverse function. I've just transformed the logarithmic form into an exponential form. But what I have to do now is swap the x and y right here, interchange those, and that will create my inverse. And so we'll go ahead and do that. So I'm going to have 5 to the power of x minus 2 is equal to y minus 1. And now this is my inverse function, and I'm going to clean it up a little bit by adding 1 to both sides. And I'm going to put my y on the left side. I just like having it over there. And so now we're going to have y equals 5 to the power of x minus 2, and then a plus 1. And so what I want to do here is make a table. And then once I make my table, we'll swap the x and y values, and that will be my table for my original logarithmic function that I'm trying to graph here. So let's see. I want to plug in values that will make my power equal to -1, 0, and +1. So I need to plug in a 1. If I plug in 1 for x, 1 take away 2, that would give me that -1 power, and then +1. And I'm going to have to do a little algebra to clean this up. So this would become 1/5 plus, and I'm going to write that 5 as a, I'm sorry, I'm going to write the 1 as a 5 over 5 so I can have a common denominator, and that would give me 6 over 5. So there's one of my ordered pairs for my inverse function that I have right here. Then let's see, then I'm going to plug in a +2, because when I plug in 2, I'm going to get 5 to the power of 0 and then +1. Well, 5 to the power of 0 is actually a 1. 1 plus 1 equals 2. So there we go. I got a second point. And then my last point, I'm going to plug in a 3, which would give me 5 to the power of 1 and then +1. Well, 5 plus 1 is 6. So this is the inverse table of the function I wanted to graph. And so now what I'm going to do, so I'm going to make another table here. We'll call it x and f of x so I can distinguish the two. And we're going to flip the x and y values. So now my x value will be 6/5 and my y value will be 1. And then when I flip the 2, they happen to both be 2. So that's fine. And then now this will be a 6, and this will be a 3 for my y value, or my f of x value. Now I'm ready to graph those 3 points. So 6 over 5 is about, or it is 1.2, which is about right here, and then up 1. So over 1.2 and then up 1 spot, so roughly about right there. Then I'm at 2, 2, about right there. And then I have one at 6, 3. 6, 3, about right there. And then we'll just kind of make a little rough sketch of this going towards my guardrail, my asymptote. And then this one curves up like that. And the domain, we already gave the domain, it's greater than 1, but they're going to want you to give that in interval notation. And so that would be from 1 to infinity right there. All right, let's look at another one of these. So once again, I'll kind of start off with the domain. So x plus 3 needs to be greater than 0. So we'll subtract 3 from both sides. And so I get x is greater than -3. And so that is where my vertical asymptote is going to be located right there, is at x equals -3. And so now I'm ready to do that process again. So I'm going to start out by just using a y for my function notation. Just makes things a little bit easier in trying to find my inverse. So now I have to isolate the logarithm, and I don't want that negative in front either. So I'm going to start by adding 1 to both sides. And so to deal with that negative in front right there, I'm going to go ahead and divide both sides by -1. And what that does is it causes a sign change of everything. So now this will be -y minus 1 equals positive log base 4 of x plus 3. And then now we're ready to convert this into exponential form. So this is going to be 4 to the power of -y minus 1 is equal to x plus 3. Now I'm still my original function. I just manipulated it to where now I can go ahead and swap the x and the y value, interchange them, okay? And that will create my inverse, okay? So now I'm going to have, and I'm going to flip the sides here. I'm going to have y plus 3 equals 4 to the power of -x minus 1. And then the last thing I want to do is go ahead and isolate the y completely. So I'm going to subtract by 3 on both sides. I'm going to end up with y equals 4 to the power of -x minus 1 minus 3. And then just like the previous problem, what we'll do here is we'll make a little table for this. So right here. And then once we have those table values, we're going to go ahead and switch them to have my table for my original logarithmic function at the top. So we want to pick an x value that will make my exponent -1. So that will be easy. The first one will be 0 because then it'll be 4 to the -0, take away 1. So I'll end up with 4 to the -1 power and then take away 3. And so then this becomes 1/4 minus, and then this 3, I'm going to put that as a 12 over 4. 12 divided by 4 is the same thing as 3. It gives me that common denominator. So then I get -11 over 4, which as a decimal, because this might help on the graph, I'm going to go ahead and list this as a decimal also. That would be -2.75. So that might just make it a little bit easier when it comes time to graph that so I can have a better feel for it. Okay, so then the next value that I'm going to plug in, let's see, I'm going to plug in, now I want to get a 0 here. So this is where it gets a little tricky. I'm actually going to plug in a -1 because what happens is I'm going to get 4 to the power of -1 minus 1 and then minus 3. Well, that double negative right there will become a positive 1. 1 take away 1 will give me 4 to the power of 0 minus 3. And then that will give me 1 minus 3, which is a -2. So now I've got that value. And let's see, I need one more. I want that to be a positive power of 1 up here. So once again, a little tricky. I'm going to have to plug in -2. And what that will do is then I'm going to have 4 to the -2 minus 1 and then take away 3. And so what we have here is that double negative will turn that positive 2 take away 1 would be 4 to the power of 1, then minus 3, which then would give us a 1. Okay, and so now we're ready to go ahead and switch these values here, and that will give us our table for our original logarithmic function up above. So I'm going to go ahead and see if I can see it all up here. Okay, I think I can fit it up here, and then I'll scroll up a little bit more. So x, and I'll call it f of x so we can remember that that's the original function. And then we have to flip-flop it. So this is going to be -2.75 is paired up with 0. And then -3 is paired up with -1. And then, oh, I'm sorry, not -3, -2. Let me fix that. -2. There we go. And then +1 is paired up with -2. There we go. So just flipping those right there. And so that should be my table for my inverse, I mean, for my original logarithmic function here. So here we are. So this is going to be kind of interesting. It's going to, that negative in front actually causes a reflection across the x-axis. And so what you're going to see is when I approach my vertical asymptote, I'm actually going to be going up this time. So let's see, at negative 2.75, I'm at 0. Let's do a different color. So about right there. And then at negative 2, I'm at negative 1. And then at positive 1, I'm at negative 2. So you can kind of see that created that reflection. And so the graph is kind of like upside down to what we've been kind of used to graphing. And there we go. And then last, I'll just give my domain again in interval notation, which would be from negative 3 to infinity. All right, I've got good news. We got one more page of graphing, and then after that, we're not going to be graphing in the next section. So, okay, so what we're going to look at now is graph the following natural logarithmic functions and include the vertical asymptote and range. Once again, that should actually say domain. All right, and so note the boundary value of the domain is the vertical asymptote is located on the graph. So wherever that boundary value is, and so we've already talked about that. So what we're going to do here is transformations might actually be an easier approach. And so I actually kind of alluded to some transformations in some of the other ones we've been graphing. And so that if you add or subtract to your logarithm, that's going to shift you up and down. If you add or subtract directly to your x value that you're evaluating in the logarithm, that's going to shift you left and right. But just like our other transformations, it's kind of the opposite of what you would think right here. So if I'm actually adding to x, it actually causes me to shift left. And if I'm subtracting, it actually causes me to shift to the right. And so it's a little counterintuitive on that, but that should be um, that should be like how our other transformations were, so that should be consistent. And then here, that was that negative right there that I told you about that we would reflect across the x-axis, in which we did. It was kind of upside down, right? And then if we have the negative directly with x, then that causes us to reflect across the y-axis, and we saw one like that too previously. So what we can do here, we don't have to get too crazy. We just need to pick a couple points to use our transformations. So I'm just gonna, I would think, obviously we'll use 1, 0. That's an easy one. And then let's see, another good one would be maybe 3 and 1.1. That would probably be a good one. And then honestly, I think I'm going to be fine with just using 2 points. So let's just use those two because we should have a pretty good feel for how these look now. And remember, base E is roughly 2.7. And so that's close to a base 3, right? So this shouldn't really be any different than a lot of the other ones we've already been graphing. So what I'm going to do here is I'm going to go ahead and put like a little at 1, 0, I'm going to put a little point here, and then at 3, 1.1, I'm just going to put a little dot right there, and then we're going to use our transformations here. And I only have a couple of these for us to look at. We're not going to get too crazy. And so right here, this is actually going to cause us to shift left 2. Remember, it's the opposite of what you kind of think. So we're going to shift left 2. And then also, this one's pretty easy because remember your domain what you're evaluating here has to be greater than 0. So you can see that, yeah, my boundary line, my vertical asymptote is going to be at x is equal to negative 2. That's where my vertical axis is, vertical asymptote is at. And my domain, might as well just list that now. My domain is from negative 2 to infinity right there. Now, all we're going to do is move these points to we're going to shift it to the left too. 1, 2, so that point's going to end up right here. And then this point, we're going to shift it 1, 2. It's going to end up right there. And then just, give a rough sketch. It's fine. On the homework, it should be pretty easy. It's going to be just like the other ones on how to apply this. Okay, so not bad, right? Now, you might be thinking, well, why don't we do transformations on all of them? Well, because on the previous couple, we had a bunch of different bases. Sometimes it was base 5, base 6, base 2. And so here we're being consistent with base E. And so I'm just going to use the basically the parent graph right here for my transformations. Okay, let's see. I've got two left. So if we look at B, once again, I'm going to put those points right here. So we have one at 1, 0, and then the other one was at 3, 1.1, right? About right there. So if you look at this, well, let's see, my domain is just greater than 0, so my vertical asymptote's just going to be right there at I'm sorry, x equals 0. And then my transformation this time is going to be going up 2. So we're just going to take these points and move them up 2 spots, up 2 spots right there. And then we'll go ahead and draw this towards my guardrail. And then this just goes up very slowly, just like all the other ones. And that's it. And so my domain for interval notation would be from 0 to infinity. And that's it for that one. And then the last one we're going to look at, we're going to have that reflection, which we actually saw one like this just a moment ago. But this is going to cause us to reflect about the x-axis. Sometimes I like to say across, but on your homework, I believe they use the term about. They reflect um, about the x-axis. And so here we are. So, oh yeah, domain. Let's go ahead and get that out of the way. So x is greater than 0. That's pretty simple. So that's where my vertical asymptote is going to be at x equals 0. So my first point was right here at 1, 0, and then the other one's at 3, 1.1. Well, my first point's actually on the line of reflection, which was the x-axis, so that first point stays put. The second point, what's going to happen is it will reflect across down below right here at negative 1.1. And so when I draw my graph, it's actually the asymptote is going up instead, going up towards the guardrail, and I'm going down like this pretty slowly. And there we go. And then the last thing is my domain in interval notation would be from 0 to infinity. And so that's going to include the graphing portion of this unit. So the next section, 4.4, we're going to look at more of like an application of using logarithm functions. And so I think y'all will like that.